So one thing I want to let you know is I just posted the grades for exam 1, as well as homework 2 through 3, and you can check it on my courses. If you have any questions, just let me know, and we can schedule a meeting, and discuss about. Also, another thing is I will post the last homework after this class. And yeah, pretty much we will finish the lectures today. Also, if you have a chance, please go and check your RIT ID cards to open the door of Brinkman Lab. I just request the access of you guys to the lab, and just check if it works or not. If not, just let me know, and I will talk with the manager of Brinkman Lab again and let you to access the lab anytime during the semester. All right. Any questions?
I have a quick question.
Yeah.
You mentioned in a different class that you would be combining the exam 2 and the final or something like that. Does that mean the final is worth more or exam 1 is worth more? How are you doing the grading now?
Oh, so basically there are 3 exams, right? So that will be each of the exam will be I mean, originally I have 3. So each of the exams takes 1/3 of the grade, of the grade under the exam category. Now there's exam 1, then there are 2/3 of grades remaining for the final exam. I call it final, actually it's a combination of the last 2 exams. So it's the weight will be twice as the exam 1. Does that make sense?
Yes.
Okay, good. So also the content covered by exam 1 will not be tested in the final exam. So that's basically, I just want to, you have learned and you have a test, and once you have complete the course, you just get a test about the remaining part. All right. Any other question?
Will you be posting any of the solutions for the assignments, or do we have to just like talk to you in office hour about the homeworks?
I'd prefer to post the solutions. I will post it. Yeah, that's good point. I will post it, and also I will be staying in the office hour for questions this week. All right.
And regarding that last homework, that's going to be homework 5.
Yeah.
Because I remember last class you said you were going to post the homework for the metal lecture, but you never did.
Yeah. So good. That is because when I checked the homework, I thought there will be a whole lot for the metal, but actually when I checked the homework, it's kind of it's not enough questions. So I'd rather to combine it and merge it to one homework. That's the last one.
Gotcha. Just wanted to make sure we weren't skipping homework.
Sure. No. Of course, no. Sorry for not notifying you about this, but there's no problem for the homeworks. I mean, everything will be covered. Especially similar questions will be tested in your exams. All right. If you have no more questions, let's continue our introduction about the sheet lamination process of additive manufacturing. Just 1 second. All right. So we have discussed two processes in the sheet lamination. And the third one is called the polymer sheet lamination. So this Solido machine would process the thermoplastic films. So what it does is it will selectively print some material which can be considered as the anti-glue in the area where you do not want to have another layer to stick to. And then a glue will be applied to this layer. Of course, the region, the area with the anti-glue will not be attached to next layer. Then a knife will cut, again, a cutter will cut out the layer's contour. This process will be repeated again and again until the last layer, the top one, is printed. And the support film material will be peeled away, just like what you saw in the previous two printing process. So that's how this works. It's basically the idea is still to print the contour and attach the layer to next one. And there are different mechanisms to realize this process. And specifically in this one, an anti-glue is applied to prevent the adhesion between some of the region to the next layer. That's how it works. So we can take a look at the video.
First, insert the engineered plastic roll into the printer. The engineered plastic roll used in the SD300 Pro is both durable and economical, giving you attractive build cost per model. Second, insert the glue cartridge. Third, insert the anti-glue cassette. Finally, place the 3 anti-glue pens. Now just hit the build button on the provided SDView software and your printer is off. Finally, a 3D printer you can afford. The model is created by layers of engineered plastic. Following sheet lamination, the cutting knife goes to work directly from your CAD data. The engineered plastic roll is layered using special glue, resulting in strong yet flexible models. The anti-glue pens then apply masking fluid for easy support removal, allowing even the smallest details to be created. Reducing development costs and time to market. Models are designed down to the smallest detail, and the engineered plastic roll is available in transparent or opaque colors. You now have your finished model in hand, ready for evaluation, without ever leaving the office.
Well, I would say it's a little waste of material, right? So for such a big kind of a block, only this small piece is taken out. So it's a little wasting of material, but that's how it works. And so basically, the parts can be built is limited to the thermoplastic material, and also there could be some post-processing to remove the adhesives or the glues, right? Basically, these glues can be completely melted in the solvent. and such that they could be removed entirely after taking out from the printers. Because it's a thermoplastic, so you can imagine the material cannot bear too high temperature, right? And also the material property compared to other, I would say, a better plastic or polymer material is limited. It's similar to what we had in the fused deposition modeling machines, because it turns out the material is very similar to what we use there, right? Also, there are some composite sheet laminations. So what it does is there will be a inkjet printing head applied to deposits the polymer powder onto the printed sheet, and then some of the dry polymer powder will be removed. Also, the stack sheets it will be heated up to make the material to be melt, and then these layers will be compressed and stick to each other. And after all, the unbonded portion of the sheet fibers will be removed, and turns out you will have a final shape. So by doing so, you have a different material combined together, such that you will have a polymer object, right? So this machine we talk about here is the impossible objects machine, and actually there's a one in our lab, which is in the end of the Brinkmann lab. I mean, there's a door over there, right? And you get in there, there is an impossible object machine sit there. And let's take a look at the video.
Impossible Objects technology enables additive manufacturing of fiber-reinforced composites for making production parts. The CAD model is sliced into layers, and each layer is converted into a digital bitmap. Layers are printed onto fiber sheets using a clear fluid and thermal inkjet technology, and a high-precision positioning system guides the inkjet heads. Polymer powder is applied to the fiber sheet, adhering to the printing fluid. Excess powder is removed, leaving behind polymer in the shape of the bitmap. This process is repeated for all of the layers of the part. Sheets are stacked, heated to melt the polymer, and compressed to consolidate the part to its designed height. Through a mechanical or chemical process, the uncoated fibers are removed, revealing the part.
So that's how it works. So compared to the Solido machine, the impossible objects machine could produce those object with fibers, polymer fibers inside. So in that case, the object is reinforced. It has a much better mechanical property of the part. Also, there's a InventionTech machine, which is similar to the impossible objects, producing those the fiber reinforced objects. So there are some other processes using the wood sheet, right? Basically, you just CNC each of the layer and attach them together, and turns out you will have a whole object made of the wood in this case, right? Still layer by layer, very interesting. So there are some other, I would say, more advanced technology like the one shown here, which is a ceramic material sheet lamination. So basically, similar to what we have previously, the only thing difference is in this case, the ceramic is utilized and the laser material is employed to cure the kind of producing to produce the contour of each of the layer. And also there's a post-processing process to solidify the parts. And also, this process can apply to metal material, this stainless steel material as well, to produce the high grade part. Also, as I mentioned, metal is another possible material for the sheet lamination, and one of the process is utilizing the ultrasonic waves. So it's similar to the welding process, but in a layer by layer manner. Let me try to play the video. Yeah. See? The ultrasonic wave is used to melt the material and attach to melt the metal sheet and attach to the build platform, and then another layer is add on to the newly built layer, and so on and so forth. So there is another subtractive process to produce those features. It's basically the combination of subtractive and additive processes and they work together to produce of metal parts out of the sheet metals.
Professor, I have a question.
Sure.
I don't understand in the ceramic process. How are the pieces joined using ceramic sheets? Because I don't understand if only the heat and the compression solidified the shape.
Yeah.
So, or you use anything?
There's I'm sorry, I skipped the details, but there is a binder. Basically, it will be glued together, just like the powder-based, ceramic powder-based processes. So yeah, there will be a binder to see. Yeah, this basically in the let me draw here.
It's just because in other the sheets you have that you can add zirconia, for example, and these are one kind of biomaterials. So it depends of the binder if it's compatible or not. So for that reason is my question.
Oh, that's a good question. So for that, I'm not so sure about whether the binder is compatible or not. But let me give you a little more sorry, a detailed explanation here. So there will be a binder coming in here, and it turns out you will have a whole parts built after you produce the contour at each layer and attach them together, and it turns out you have the final parts. And there is a debinding process like the one shown here. So it's basically you heat it up in an oven, and the binder will be removed turns out you have a finished component, just like, very similar to the selective laser sintering for those ceramic or even selective, for the polymer or the ceramic powders. So there will be a debinding process to have the final part. So in such a case, the binder will be removed, and I'm not so sure about the biodegradability of the binder, but after all, they will be removed, right? And I suspect that shouldn't be an issue for these kind of parts to be adapted in those medical applications. But I'm not sure because I didn't look into the applications for this part. But I do see some of the processes is aiming at producing the parts for medical applications. So similarly, I think this process can also be used in such applications.
Thank you.
Mm-hmm. So I think that's, I mean, for this process, I don't want to put too much time on it. So I think I might stop here so you can go through the details yourself. But overall, I think you should get the basic mechanism for such a process, the sheet lamination. So instead of starting from powder or starting from the filament, this process starting from each of the sheet, and for each of the sheet, it basically it's one layer, right? You can create the contour of that layer and find some way to combine different layers together. In this case, it's usually a glue or binder, and then remove the excess material. Also, sometimes you want to do a debinding. Not all the process has the debinding step, but definitely some of the ones required. And after all, you have a whole solid parts. So that's the idea of the sheet lamination process. And different ways to combine the layers and cut the contour and remove the excess material basically are introduced under this umbrella, this sheet lamination processes. All right, and we can talk about the last lectures, which is, let me open it up. Which is some of the fundamental knowledge about the mechanical and electronical components of a 3D printer. Just imagine you want to build up your own 3D printer. How you're gonna start, right? So we have learned different processes so far, and you can see there are quite a bit common points for the hardware, software, also the mechanisms to realize the process. So let's talk about some of these common points for 3D printers. So in a 3D printer, the brain of a printer is this so-called microcontroller, right? So this microcontroller is integrated a circuit, a board with different components with different functions. As you can see here, there are each of these components or ports or port is corresponding to some of the functions, like the one, this region is for the power supply, and here there are the heat beat, and also there are powers for the extruder heater. And here these pins are used for the extruders motor. Similarly here, also there are XY tables motors over here and the Z motors. So all these components work together to control the motion of the printing platform, the printing head, and to heat up the printing bed and the printing and the nozzle to realize the whole process. There are some popular microcontrollers like the Rambo, Duet Wi-Fi, and a Smoothie board. And I think if my memory is correct, the PUSA is using the Rambo board, I mean microcontroller. And there are quite a bit open sourced codes or some of the applications based on these microcontroller. These are very popular ones. Many low-cost printers just utilize one of these. So there are some other components which are very important in the printer, but at the same time, you might not pay enough attention to it. For example, these axis and stop. So the purpose for having such stops is to detect when the item move along one axis, whether it reaches the end of I mean, whether it reached the ends of the axis, the limits of along this axis or not. So basically, 3D printer needs to know this information such that it will stop the motor, right? So there are different sensors, and based on its working principles, we can clarify them to mechanical based, optical based, and magnetic based. And basically here shows some of the, where's my mouse? Okay, yeah, here shows some of the pictures of these stops, right? Sensors, stop sensors. So there are different states for the sensors. So if a no is the state, that means it means a normally open, right? It stands for normally open. It's not a no, it's a normally open instead. That means the voltage across the pin will go from 0 to 5 volt. Or there is a normally closed state, which is NC for short. And that is basically the voltage across pin will go from 5 to 0 when the sensor is actuated. So basically it can be considered as two opposite states, normally open and normally closed. And no matter how these sensors based on, it will give you such a states for the printer's microcontroller to make judgment. Also, there are temperature sensors, right? Yes, some thermistors, thermocouples, and some of the RTDs. Why we have different sensors? That is because each of the ones could be used in different temperature ranges, right? Because there are different processes under different temperatures. So you have to find the one which is applicable for such a temperature. So that's why we have some thermistor, RTD, and thermocouples. And if you ever learned about the material processing or other courses, you should have some ideas about the the working principles for these sensors. And let me just skip the details. You can check it yourself. Another thing is the control of these mechanical mechanical parts, as well as the temperature control. So the PID control algorithm is a widely used one, which is robust in many control applications. And this is also used in the control of the temperature for a 3D printer. So the advantage for this is, again, it will control the the temperature of the heated elements, or the printing bed, or the printing head in a quick responding time, as well as it will have it has no overshooting happening. And that's a very important thing in this case, to have a PID control in the temperature control processes. And in many of these 3D printing process, the temperature control is the key, right? So that's why we really want to have a very robust temperature control. Sorry. Another thing is the motion, right? The motion of the printing platform and the printing head. So there is a problem, is so-called the positioning resolution. That means the minimum distance, the smallest distance you can ask the motion system could move in any direction, right? Basically, this kind of positioning resolution is controlled by the motor, the pulleys, and the pitch of the screws, and so on and so forth, right? And there will be a more detailed introduction in the following slides for all of these factors. How could this affect the positioning resolution? And the motion, as I mentioned, is expected to be controlled in a feedback control loop, such that if something happens, the control algorithms will make adjustment according to what it receives. And turns out this control strategy will be more robust over those open loop control. So that's why the closed loop control is more desirable. It takes the feedback and make adjustment, and such that the motion will be in a more stable way in the process. So there are different motors for the 3D printing systems. We have the DC motors, servo motors, step motors. So for the DC motor, when the voltage is applied, then the motor turns, right? So the speed of motor is proportional to the voltage. And the servo motors, there will be an encoder. Basically, encoder will control the motion of the motors. And step motor, basically the motor is operated by a synchronized pulses, and that will cause the shaft of the motor to rotate in a fixed steps. So basically, and from those descriptions, we can tell there will be more control of the motor for the servo and step motors, not just the simple DC motors, right? Although the step motor can be considered as a combination of DC motor together with some of these synchronized ports, right? But still, for a simple DC motor, there are no such a control. Basically, you have no fixed step, right? And the servo motor is more accurate. Basically, there will be a encoder involved in the control, such that you have a very precise control of the of the rotation of the motor, and turns out you have a very precise control over the motion driven by the servo motors. So as I mentioned, for a step motor, a pulse is utilized to control the motion. And basically, when you talk about a pulse, that means some discrete signals. That will be a time period in between of the two pulses. In that case, when a pulse is received, the motor will rotate their axis, and in between of the pulses, it will be static. So that's how this step motor works. Basically, in each step of the motion, the motor will have a rotational increments, and that is the minimum motion this motor could provide. And that's how the positioning resolution is realized by the step motors. So as you can see here, we have this illustration, and you can see the motor is rotate in such a way, and in each of the rotation, the motor just move a small angle, and that is the smallest motion this motor could achieve. And in this case, the smallest angle is 1% of the whole of 2 pi of 360 degrees in this case. So that means the positioning resolution for this motor is such a 3.6 degree. It will take 100 steps to make a full rotation, to travel 360 degrees in this case. I think we can stop here. Let's come back at 10. All right. Okay, let's continue. So again, in this illustration of step motors, you can see there are four, sorry. There are four electromagnetic, electromagnet over here. So these four electromagnets will be energized one by one. And once this is energized, it will attract this gear to move. So for example, when this first electromagnet is energized, it attracts the gear to move a certain angle. In this case is 3.6 degrees. And then the second electromagnet is on and the first one is off. Then the gear moved another 3.6 degrees. It happens for this third and fourth electromagnet. And that's how the whole motor rotates. And as you can see here, it's not a continuous motion. Actually, it's discrete, but because of in between of the two rotation, the time is very short. So in that case, you just think it's a continuous motion, but by principle, it is a discrete motion. And there's a step, which is in this case, 100 steps per revolution. And turns out you have 3.6 degrees for each of the steps. All right. And let me try to play this video.
The stepping motor can be controlled by a micro-step drive technique. The micro-step is a technique to electrically segment the step angle for reducing the vibrations and noise of the stepping motor. Now we will see the operating principles using the 90-degree step model. The power of the magnetic field where the electromagnet is generated is in proportion to the current size flowing in the coils. We will turn on the 9/10 current in the S1 coil and the 1/10 current in the S2 coil. It is drawn a little towards the S2 coil by the amount corresponding to the variance, and then stops rotating after a little. If you change the ratio of the currents, you can drive with a smaller step angle than conventional step angles. It is possible to break the basic step angle of 0.72 degrees down to 1/250th, which is 0.00288 degrees. This technique allows you to use a minute angle feed for smoother operations. This is ideal for applications which prohibit vibrations or noises, or require a minute angle field. This is also good for applications to reduce uneven rotations at low speeds.
All right, as you can see here, by manipulating the current for each of the coil of those electromagnets, a micro-stepping could be achieved. And it will reduce the noise and vibrations because you have control on the motion of the motor in much smaller steps. And that could make these micro-stepping desirable. And also you could have much smaller steps compared to the original step angle, right? So let's say you have a motor with 20 steps per revolution. let's say you have 200 steps per revolution. Then how many degrees will motor turn per steps, right? So because you have 200 steps per revolution, and for one revolution, it travels 360 degrees, right? And in this revolution, there are 200 steps, right? So it turns out gives you a let me see, yeah, 1.8 degrees per step, right? That's how you compute these kind of steps. Compared to the actual steps of a step motor, for the macro stepping, it moves a fraction of a step at a lower power. For example, if you could have a 1/22 macro stepping, that means you could rotate the motor 1/22 of a step when this macro stepping is utilized. So for in this case, you have 1.8 degrees per step, right? I mean, then for macro stepping, you will have 1.8 over 32 degrees per step for the macro stepping, right? You can compute how what the number it is, but that's how you tell if you have such a macro stepping numbers, right? Also, there are standard step motor sizes. It has a family of step motors, and basically those dimensions and sizes are standard because you want to, I mean, in different applications, you just want to select ones fit to your need, right? And there are different ways to I mean, there are different motors like these ones you could select for your applications. There could be some sensors which is called the rotary encoder, and these sensors can be utilized to detect the rotation by checking those light patterns. Basically, it here shows you a illustration of a rotary encoder, and it has when the motor is rotating, the pattern of the encoder will be different at different position. Sorry, I mean, when the motor travels different angles, these kind of pattern is different, and each of the pattern, the shadow and the light pattern, bright pattern, will give you a state. By checking this pattern, you could tell what is the angle the motor rotates. So that's how it works. And there are different ways to detect, to realize this detection. You can have a mechanical, optical, magnetic, and capacitive rotary encoders, but still it will check these patterns, and through these patterns there will be a state associated with the angles. So for the motion stage, basically there here shows you a typical ones for the Prusa, right? And there are different axes, X, Y, and Z motions. And you can see there are rails, pulleys, and also these kind of motion platforms assembled together. And when you have a physical built platform, you want to associate with these physical directions with the one you have in the software, right? There are different accesses for the physical printer. So for example, like the one shown here, right? So pretty much this and this would be X and Y, and along the, so perpendicular to this plane, there will be the Z directions, right? So for the XY stage, usually there will be a belt and pulley together with a step motor. So that will be used to control the motion of the belt and the pulley. Also, there are rails and bushings. Basically, the positioning resolution of the XY stage motion is pretty much determined by the step motor's resolution and together with the pulley's diameter. And for the real support systems, a big problem for it is the frictions. So basically, if the friction of the rail is too big, that will definitely affect the stability of the XY motions. So that's why there are some bushings which are the self-lubricant bronze. So for such kind of bronze, basically there are small pores on the surface, and for each of the pores there will be lubricant applied prior to the assembly. And basically, these are very small pores. So in that case, the oil will be always there. The lubricant will be always there. So such that you do not need to actually apply the lubricant once again. So that's how this self-lubricating bronze bushing works. Also, the stainless steel rails need to be polished, right? And also the material itself is stainless. Again, the friction is critical. So you want to always minimize the friction. That's why you want to polish the rails and use the stainless material to prevent the friction from the rust, right? And let's look at some of the calculations for the belt and the pulley. So as you can see here, if we look at the black dot, that means there is an object attached to the belt. Then you have a motor attached to drive the pulley, and it rotates at some speed. Let's see, it has an N revolution per minute, right? That's the rotation motion, right? And if you have a diameter of the pulley dp, then for each of the rotation of the motor, how far will the black dot moves? So to compute that, you just think of for each one of the rotation, right? Basically, this pulley will also rotate basically one rotation, which is a pi, I mean 360, right? If we use the radiant, that's pi, right? That means this point travels travels pi times dp, which is the travel of this point. And this one and this one during the travel, these two stays relatively static. That means at this point, it also travels this much. So that is the motion of the points, pi times dp millimeter per revolution, right? That's one revolution, right? Then how about you have n revolution, right? Sorry. If you have n revolution, what you essentially have will be n pi dp, right? That's but n, if there should be a unit for n. If let's assume the n will be revolution per minute, and this is millimeter per revolution, and it turns out you will have pi. Sorry, let me erase. You will have n pi dp and millimeter per minute, right? That's the speed of this point. But the thing is, we usually use millimeter per second instead of minute. What you want to do is you want to convert a minute to a second, right? So what you will do is for 1 minute, right? 1 minute, there will be 60 seconds, right? And you cancel out the minute, and turns out you have 60 and n pi dp millimeter per second. That's the speed of the of this point. If you are given a motor with n rotation revolution per minute, and the diameter of the pulley is dp. That's how you come up with the speed at this point, right? So there will be another thing you want to keep in mind. That is the rotation. I mean, that is how you install the motor together with the pulley. Usually, if the motor is directly attached to the pulley, that means when the motor travel 1 revolution, the pulley will also have travel 1 revolution, right? But I mean 1 rotation. But there could be some gears in between of the pulley and motor. For example, if there's a gear attached to the motor and then to the pulley, and the gear has a ratio 1/3 1, 2, 3. That means when the motor travels one rotation, the pulley will travel 3 rotation. So in that case, the revolution per minute need to be converted. For example, if originally the motor, you have the number n, oh, that's too bad. let me rewrite it. You have the motor have a n revolution per minute and a gear ratio to be 1/3. And it turns out for the pulley, you will have 3n revolution per minute. So that is what you want to keep in mind before you start the computing. For example, the speed at this point. Any question for here? It's clear, right? So I think we have derived this, right? But I can rewrite it again. And again, let's assume the motor is directly attached to pulley, right? That means one rotation for motor, there will be one rotation for the pulley. And there's n revolution per minute. Again, for each of the revolution rotation, this dot travels pi dp, right? But still, you want to do some unit, right? Units conversion, and that's n revolution per minute, and the pi dp, that's that is millimeter per revolution. And again, convert the minute to second. That will be n. First, you just cancel out this n pi dp millimeter per minute. And turns out you have n pi dp millimeter minutes and times 1 minute over 60 second, right? And that becomes 60 n pi dp millimeter per second. That's how you come up with this speed, right? And you want to memorize how you derive this, right? And again, if there's gears and with certain gear ratio, this may not be n, right? It depends on the gear ratio, and you want to change this rotation here, and turns out the result will be different. And that could be questions asking you to derive this, but with some gears in between of the motor and the pulley, and then you want to use the gear ratio to come up with the right rotations for the pulley. Or there could be some questions with this travel speed known, and this diameter known, gear ratio known, and asking you to come up with a motor turn speed, which is the revolution per minute. Then it's a total reverse way, right? So you should be able to do so by reversing this deriving. derivation, right? Yeah, that's how you come up with. Again, as I mentioned, that if you already know the speed, also the diameter of the pulley, also you know whether this pulley is attached to motor directly or indirectly, I mean, no matter either case, you directly or indirectly, if indirectly you have the gear ratio known, then you should be able to derive what is the n should be, the revolution per minute should be, right? That is what you could reversely derive it. And another thing is, if you know a distance instead of a speed, right? Now the question is asking you the revolution you should have for the motor, right? I mean, again, that is what you want to derive, similarly to here, right? You've already know the dot moves this amount, pi dp, millimeter per revolution, right? And you have a distance this much, x. That means when you want to travel this amount of distance, the revolution needed is x over pi dp, right? So that's how many rotation this pulley should have in order to travel this x millimeter. And again, if the motor is directly attached to pulley, this will be the revolution of the motor has. But if there's a gear, then use the gear ratio to find out the revolution the motor has, right? That's similar to the previous two deriving. In the z-axis, it's a little different. Instead of pulley and instead of pulley and also the rails, this kind of a cantilevered platform is utilized, and the key part is a screws. So the screw will convert the translation along the direction to a rotation along this screws, right? So the basically basically the pitch of the screw will decide the positioning resolution of the Z motion. So given the pitch of this lead screw, and this one is directly attached to a motor, then how many motors revolution are needed to move the knot distance of x? So that would be a very interesting question to derive. So in this case, the motor is attached to this lead screw directly. That means one revolution of the motor will travel this pitch distance. I think I forgot to mention, basically the definition of a pitch is if you rotate one turn, how many distance it travels, that's the pitch, right? That the pitch decide. So in this case, for one revolution, there will be p millimeter travels along this axis, and that's one sorry, that's one revolution. Then you want to travel x, then basically you just put the two together, and it turns out the production of these two will give you how many revolution requires, right? That's how you compute the revolution. But here again, we'll assume the motor is directly attached to the lead screws. So if there are gears, you have to use the gear ratio. In that case, one turn of the motor will not lead to one turn of the lead screw. It will be determined by the gear ratio. So in that case, use the gear ratio, right? So give the pitch of this lead screw, and again assume the motor is directly attached to the lead screw. Then let's compute the motor speed, which is the n revolution per minute. And also what you know in here is this velocity of the motion of the knot. In that case, you have v millimeter per minute velocity, right? And also you know one revolution will lead to p millimeter motion. That is determined by the pitch. And it turns out if you have the two combined together, what you have will be the revolution per minute of this screw. And also we know the lead screw is directly attached to the motor. That means the revolution of the screw is 1:1 to the revolution of the motor. And turns out you will have this revolution per minute, which is the revolution of the motor, right? That's how you derive it. And that will give you the idea if there is not a directly motion, instead of instead we have pulleys, belts, or some gears. That will change this. Will change this computation by converting the revolution of lead screws to the revolution of the motors, right? Well, once we have understand the motion of the XY platform as well as the Z-axis, the cantilever structures. So let's go through the process. Once you have designed your object, right, and you fit it in the CAD file to the slicer, and then the G code will be generated from the slicing software. Basically, the G codes tell you how you're gonna move in the XY plane as well as in the Z direction. So it turns out during the printing process, the belt and the pulley are utilized along the X and Y directions on the XY plane. And all the lead screws is utilized to lift up either the printing platform or the printing head, and such that you will have a X, Y, Z 3-axis motion in this case. And here gives you some of the example of the G code. I mean, if you ever took the CNC machine courses, you will see it's very similar, right? It's the same thing. The G code is also utilized in the CNC machining, and you can find all the information through this website to explain each of the command. And there are some customized command, means you could define your own motion under that command. Okay, let's see you have lead screw with 16 threads per inch. And it is connected to a step motor with 1.8 step angle. And now you want to move the knot with a distance of 1.5 inch at a speed of 10 inch per minute. Then how you gonna compute the steps a motor must turn, right? And also what speed should the motor be turned, right? Also, that will be the combination of all the information we have learned about the motor, step motor, the sorry, the lead screw in the Z direction, also the pulley and the motor in the XY direction. So let's take a look at it. So here, it does not directly give you the pitch, but you should be able to find it out, right? So 16 threads per inch, that actually gives you enough information to find out the actually the pitch. In this case, sorry. Where is it? All right. So in this case, 1/16 inch per revolution, that is the pitch, right? Then the knot travels 1.5 inch. In this case, you could tell how many turns this lead screw is turned, how many revolution it has. That is 1.5 over 1/16. So turns out it's 24 revolution. And that's the revolution, right? And I think, do we have any? Yeah, directly. Okay, you see, it says the screw is connected to a step motor, and without mentioning any other like gears or pulley or so on and so forth. So that actually tells you it's a direct connection. In that case, one turn of the lead screw will be corresponding to one turn of the step motor. So that will be 24 revolution this motor turns. But in that case, it's not the steps, right? It's just the revolution. Remember, in the step motor part, the step basically is not one revolution, it's not revolution. In this case, we have the step angle, that's 1.8 degrees. In that case, for one turn, how many steps there will be? And we need to figure out. And for one turn, it travels 360 degrees. And for one step, that is 1.8 degrees. So you could easily figure out for one turn, what are the steps? That is 360 over 1.8, which is 200, right? That's for one revolution. Remember, that's for one revolution. For one revolution, there are 200 steps. But in this case, there are 24 revolutions in order to make the knot travel 1.5 inch. In that case, the overall turn, the overall steps is 200 times 24, which is 4,800 steps. And turns out you have the overall steps. Any questions for this? All right, that's great. And then another question is to computing the motor's speed in revolution per minute, right? How are you gonna do? Again, you have a speed 10 inches per minute, right? And also there are 16 revolution per inch, right? That is because basically you can use the pitch to come up with, and turns out per basically you could have per for 1 minute how many revolution this lead screw will travel, will rotate, and turns out it's 160. And again, this motor is directly connected to the lead screw. That means it's 1-to-1 corresponding, and there's no gears. So the motors also rotate in the n revolution per, in the 160 revolution per minute. And that's how you also come up with the motor speed as well. So it's a very, I would say, it looks complex, but if you have each of the piece understood, you should be able to solve it easily. So you want to go through these slides and try out these kind of questions requiring each piece of knowledge from these lectures. Also, there are some other configurations for 3D printers. So far, we talk about our or Cartesian 3D printers, meaning you have X, Y, 3 orthogonal axes. But that could be some delta printer or polar axis printer. And let me try to show you. See, this is the delta printer. If you look at, I don't know if there's a zoom view, zoom out view or not. Basically, it has a delta mechanisms. Each of the axes will move up and up and down, and one position in the 3D space could be achieved by combination of these upside down of the 3 axes. So it's a so-called the delta printer. Also, there are some polar printer, means it will move like in a polar coordinate system, like the one showing here. Here is a polar printer. See, it has a platform move in one direction and together with a rotation. And this printing head move in the X, in the Z directions. All right, that's different from those Cartesian space printers. And basically you have to do a conversion to convert the motor's motion of these platform and the rotation to certain to certain motion of which is required in the G code. So that will be some special software required associated with the printer. But it's very convenient to print those rotary shapes, like the one showing here, a cylinder, hollowed cylinder, right? I think that's pretty much all for for the lectures. And I will release the last assignment by tonight. And also you could spend your time on the final project. Again, try to use your ID card to open the door of the Brinkman lab. And I think that's pretty much for today's lecture. Any questions before I end the lecture? No? Okay.
Professor, I have a class.
Oh, yeah. Yeah, go
like,
ahead.
It's not related to this class, but it's related to 3D printers.
Oh, okay, good. So you want to ask or?
Yeah. I
Sure.
just didn't want to keep people waiting in case it was about something else.
Oh, okay. Yeah. You can stay here, and if there's no questions from others, I mean.
I have a quick question.
Sure.
That applies to everyone.
Yeah.
Will you have all the homeworks and everything graded before exam, like the final exam?
Yes.
Okay.
Yes.
Thank you.
Mm-hmm.
Okay. So for my MSD project, we're building a large scale 3D printer.
Yeah.
So it's basically a big printer. And we're trying to determine the reliability of the printer and the print builds that the printer is meant for is going to be printing continuously from anywhere from, let's see, it can go anywhere from 2 to 7 consecutive days.
Oh, okay.
And I wanted to know if there was a way, besides the filament running out, so without worrying about the filament running out, was there a way to accurately determine if the printer is there a way to accurately test if the printer will be able to print 7 consecutive days without failing?
Well, that's a that's a really interesting question. So what's the problem to prevent you actually do a printing which lasts 7 days? Let's see.
Time, because it's
Oh,
for
time.
MSD2, and if it 7 days, right? If we print exactly for 7 days, then we'll only have like 2 to 3 weeks of testing.
Yeah.
And then we might not be able to get other things in, like troubleshooting certain parts and stuff because the printer's printing.
Yeah, I mean, there are some methods to estimate the kind of a reliability or uncertainty of a process. You could have some theoretical numbers, but but without an actual experiment, this cannot be guaranteed. This is not, I would say, for many. I mean, just imagine SpaceX or NASA. they have a jet engine or a rocket engine. They will never actually use it without any testing, a real testing, right?
Yeah.
So in that case, it's really hard to justify if you just do some analysis without any experiment. For example, you said it's a 2 to 7 days requirement. So in that case, what you could do is, how about you just test a 2-day or 3-day without a full 7 days testing. With that tested together with some of the parameter, like, I don't know if you want to measure the, for example, the accuracy of the layer, or some, well, roughness, or some of those measures about your 3D prints to kind of predict how likely it will be after another 2-3 days, right? I mean, 3-4 days. So that will be more convincing. I mean, it's really hard to just to do some theoretical analysis without the experiment. Yeah,
that's what I kind of was thinking. We're basically gonna test to see if it prints, like, let's say it'll print for 6 consecutive hours, and we're printing a bunch of like testing things, such as like a benchy, or like something to test delamination or something, or like to print overhanging and whatnot, detail. So we're gonna do some tests printing that. And that would take about 6 to 8 hours, and we're thinking, okay, if it can print in good quality for 6 to 8 hours, then likely it'll print for 2 to 3 days or 7 days without stopping.
At least you have something to show. And another thing, I mean, I would say is you should be careful to use any statistic model in this case, since you don't know what is the model, I mean, the distribution for the reliability of a 3D printer. You know what I mean? So for the statistic, you have an assumption, for example, okay, the data, for example, the rate of failure or successful of this 3D printer actually follows, like, let's see, the normal distribution, right? In that case, you could do some of these analysis to figure out, okay, even I do like 7-6 hours successful printing, I can predict this and that. But without this assumption, or if you could find some paper talking about that, that's also fine. But the point is you have to have some kind of a preconditions or assumptions in hand.
That makes sense. Yeah, I totally forgot about that.
Yeah. But that's very interesting.
Yeah, it's an interesting problem. We're trying to figure out how to accurately measure reliability of something that's never been tested before, you know?
Yeah. Definitely try to find some of other works. I'm pretty sure that could be examples. As I mentioned, maybe some aerospace applications. I mean, for example, before you land on Moon, how could you tell your rocket could work to land on Moon, right? There must be some methodology to do such kind of estimation, which is, I would say, well, not confident enough or reliable enough.
Yeah. Gotcha. Okay, thank you.
Yeah.
Have a good day.
Yeah, you too. Any other questions from Peter and Andrew?
Yeah, I just wanted to follow up. You said last week that the polished clear part requirement was going to get removed from the project document, but it doesn't look like it's been updated yet.
Oh, okay. Yeah, that's good reminding. I will do it right away.
All right, thank you.
Yeah. Andrew, anything? Okay. I think this is all for today's class.